Imagine reaching Mars in just a few weeks, not months. What if intercontinental flights could be completed in under an hour, and deep space missions to distant stars were no longer a fantasy? These possibilities hinge on a new era of advanced propulsion systems that are rewriting the rules of speed and distance, both on Earth and in space. The urgency for advanced propulsion. While traditional chemical rockets have served us well for over half a century, they have significant limitations. They're slow, fuel-intensive, and limited in range. With the growing demand for faster, more efficient travel both on Earth and beyond, the need for innovative propulsion technologies is critical. For Earth-based transit, this translates to a desire for hypersonic speeds and reduced emissions. In space, it means shorter travel times, reducing risks to astronauts, and making interplanetary travel feasible within our lifetimes. Pioneering types of advanced propulsion systems. 1. Electric propulsion systems. Electric propulsion systems, such as ion thrusters and Hall effect thrusters, represent a game-changing approach to space travel. Unlike chemical rockets that rely on combustion, electric thrusters use electric fields to accelerate ions, generating thrust with extreme efficiency. Efficiency and applications. Electric engines consume far less fuel than traditional systems, making them ideal for long-duration missions. NASA's Dawn spacecraft and Artemis missions use ion engines to traverse the solar system more efficiently than ever before. Current limitations. While efficient, electric thrusters generate relatively low thrust, limiting their use to deep space missions where gradual acceleration over time is sufficient. 2. Nuclear propulsion. From Earth orbit to Mars in record time. Nuclear propulsion offers two main approaches: nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP. NTP uses nuclear reactors to heat a propellant, which then expands to create thrust. This can potentially halve travel times to Mars, addressing the need for faster missions. NEP, on the other hand, converts nuclear energy into electricity to power electric engines. It offers superior energy density and thrust compared to chemical systems, making it a contender for missions to the outer planets. Challenges. While nuclear propulsion offers unparalleled energy potential, it also raises concerns about radiation safety, reactor design, and international regulation. 3. Antimatter propulsion. The ultimate frontier. Antimatter propulsion taps into the most energetic reactions known to physics, matter-antimatter annihilation. A single gram of antimatter contains the energy equivalent of 43 kilotons of TNT, making it theoretically possible to reach the outer planets or even nearby stars within a human lifespan. Advantages. Antimatter propulsion could provide up to 1,000 times more energy per unit mass than nuclear fission, making it the ideal candidate for interstellar exploration. Current hurdles. The production, storage, and cost of antimatter are currently prohibitive. CERN's annual antimatter production would barely power a light bulb for a few minutes, demonstrating the significant gap between theory and reality. 4. Photon propulsion. Light-powered voyages. Photon propulsion involves using the momentum of photons, particles of light, to propel spacecraft. Breakthrough Starshot, for instance, envisions using powerful lasers to accelerate tiny spacecraft to 15 to 20% of the speed of light. This approach aims to send lightweight probes to Alpha Centauri, the nearest star system, within a few decades. Pros and cons. While photon propulsion theoretically allows for near-relativistic speeds, it requires immense energy inputs and advanced beam targeting technology, both of which are still in early development stages. The impact on Earth-based travel. While interplanetary travel captures our imagination, the principles of advanced propulsion can transform terrestrial transport as well. Hypersonic flights. Nuclear or electric engines could enable aircraft to achieve speeds of over Mach 5, reducing international travel times to under 2 hours. Hyperloop systems. Integrating electric propulsion in urban transit could improve speed and efficiency while reducing energy consumption and emissions. Environmental considerations. Unlike chemical rockets, electric and nuclear propulsion systems can be adapted to minimize emissions, providing a pathway to greener aviation technologies, revolutionizing interplanetary and deep space travel. The most immediate applications of advanced propulsion lie in space exploration. Electric and nuclear propulsion are already in use or development for missions to the Moon, Mars, and the asteroid belt. Electric propulsion in lunar missions. NASA's Artemis program uses ion thrusters to support lunar exploration, paving the way for sustained human presence on the Moon. Nuclear propulsion for Mars and beyond. Projects like DARPA's Draco aim to demonstrate nuclear propulsion within the next decade, potentially enabling faster Mars missions with less onboard radiation exposure for astronauts. Photon and antimatter propulsion. Though still largely theoretical, these systems could redefine our approach to deep space exploration, making multi-year missions to the Kuiper Belt or even Proxima Centauri a possibility within this century. The challenges ahead. No technology is without its barriers. While the potential of these propulsion systems is vast, each faces unique challenges. Technical hurdles. From fuel containment for antimatter to reactor shielding in nuclear propulsion, the engineering complexities are immense. Safety concerns. Whether it's radiation from nuclear engines or the risks associated with high-energy photon beams, ensuring safe deployment is a key obstacle. Political and ethical barriers. The development of nuclear propulsion, in particular, requires international consensus, given the geopolitical implications of deploying nuclear materials in space. Future outlook. Are we ready to propel forward? The potential for advanced propulsion is not just in speeding up travel, it's in transforming how we approach the very concept of distance, time, and exploration. Over the next few decades, expect breakthroughs in NASA's Artemis and Gateway programs, potentially integrating nuclear engines for sustained lunar missions. Fusion propulsion concepts, with private companies like Helion Energy leading the charge toward a new era of net-positive fusion, which could offer near-unlimited propulsion energy. Multi-agency collaborations between space agencies, defense contractors, and private innovators that will drive propulsion technologies forward. Conclusion: let's accelerate the future. Advanced propulsion systems are more than just technological advancements. They are the engines of human ambition. Whether we are expanding the reach of Earth-based travel or venturing into the vastness of space, these systems hold the key to a faster, more connected future. Join the conversation. Share your thoughts on the propulsion systems that excite you the most, or explore how you can contribute to the next leap in human mobility, whether on Earth or beyond.